method in the LM and GLM function in glm.jl module. The method argument takes only two symbols, Cholesky and keyword. The method argument controls which matrix factorization method to use. If method equals to Cholesky, which is the default one, then Cholesky decomposition method will be used. If method equals to keyword, then keyword decomposition method will be used. In this presentation, we'll empirically explore the impact of these two matrix decomposition methods on estimating parameters in linear models in terms of accuracy and performance. As we know, the efficiency of estimating regression parameters depends on how efficiently we can compute the inverse of the matrix. It becomes more difficult computing a matrix inverse accurately for an ill-conditioned matrix. The condition number provides insight into the numerical stability of solving linear systems involving some matrix A. A high condition number indicates that the matrix is ill-conditioned, meaning that small changes in the responses can lead to significant changes in the solution. For an ill-conditioned matrix, solving linear system may lead to numerical instability, loss of accuracy, and amplification of errors. Whenever the condition number above a limit or higher may indicate severe ill-conditioning, which could raise significant challenges in solving linear systems accurately. In such cases, using more stable numerical methods or considering matrix preconditioning techniques becomes necessary to obtain reliable results. Matrix decomposition or matrix factorization is the process of breaking down a matrix into a product of simple and more structured matrices. These decompositions are valuable in various areas of mathematics, engineering, and data analysis, as they simplify computation, reveal underlying patterns, and enable efficient solving of complex problems. Keyword decomposition factorizes a matrix A into the product of an orthogonal matrix Q and an upper triangular matrix R. Cholesky decomposition is applicable to symmetric positive definite matrices. It factors a matrix A into the product of a lower triangular matrix L and its transpose. Now let's start with playing with Julia GLM with two different decomposition methods, Cholesky decomposition and the keyword decomposition. First, let's include required packages. Then let's fix some random shifts so that we can reproduce the results. Now create a random matrix of size 10 cross 2 and let's fix some beta value 5 and 10. You can see that condition number of the random matrix is 3.13. This is not a very big condition number. So let's generate some response vector. Okay. So what we have done, we have created a random design matrix of size 10 cross 2. That means it has 10 observations and 2 covariates or 2 predictors. And we have generated a response vector multiplying with x beta, where beta is 5 and 10. We have fixed that beta value. Now try to estimate the beta using linear model with two different decomposition methods. Let's try with pure decomposition method. Then we'll try with Cholesky decomposition. Okay, we can see that pure decomposition method that estimates of beta using pure decomposition method, it gives perfect estimates 5 and 10, and estimates of beta using Cholesky decomposition method, it is also given the perfect estimates of the beta 5 and 10. Since the condition number of the design matrix is only 3.13, well condition, so there is no difference in accuracy using pure decomposition as well as Cholesky decomposition. I'll create a design matrix intentionally with the higher condition number. Okay, I have created one design matrix X. Now let's check that condition number of the matrix. It is 3520.4. It is in the scale of 10 to the power 4. It is less than 10 to the power 5. Now regenerate response vector and try linear model pure decomposition method. Okay, we can see that estimates of beta is 5 and 10, which is a perfect fit. Now let's try with Cholesky. So here beta estimates of beta is 5 and 10. Perfect. Now let's try to increase that condition number of a matrix. So let me take 4. 10 to the minus 4. We are generating a new design matrix. Condition of the design matrix is 35204 point something. It is in the scale of 10 to the power 5, but it is less than 10 to the power 6. Now regenerate response vector. We can see that estimates of beta using pure decomposition is the perfect estimates. Now for Cholesky also, it is a perfect estimate. Okay, so what we have observed, 10 to the power, if the condition number is 10 to the power 6 in this empirical example, if the condition number is less than 10 to the power 6, the pure decomposition and the Cholesky decomposition in the linear model giving the same accuracy. Now try to increase a bit. Now condition number is in the scale of 10 to the power 6 and less than 10 to the power 7. We are getting perfect estimates using pure decomposition. Now we can see that estimates using Cholesky decomposition is little different from that. Okay, so now increase the condition number in it. Let's manipulate x in such a way that condition number is in the scale of 10 to the power 6 and it is less than 10 to the power 7. Okay, still I am getting perfect estimates using keyword decomposition, but you can see that accuracy is decreasing as the condition number increases. The very high condition number, the matrix is, we can say, ill conditioned, but we can see that keyword decomposition method, the estimates using keyword decomposition method, still it is giving the perfect estimates. Oh, now the Cholsky decomposition method, it is giving that positive exception. That is not, matrix is not positive definite. So x prime x matrix is not positive definite. So according to Cholsky decomposition method, it is a singular matrix. Okay, so when that condition number is greater than 10 to the power 8, we can observe that Cholsky decomposition detect singularity in that x prime x matrix. Okay, but you can see that keyword decomposition still giving that perfect results. Now let's try to increase the condition number a bit. So now the condition number is 3.5 times 10 to the power 9. Let's regenerate the response vector using new design matrix. Okay, still I'm getting the perfect estimates using keyword decomposition method. And we know that the Cholsky again show that positive definite error. Okay, now 10. So it is 3.5 times 10 to the power 10, the condition number. Still I'm getting perfect estimates using keyword decomposition method. So now we can understand why we usually say that keyword decomposition is very stable method, numerically stable. Now 10 to the power 11, 22. Yeah. So the condition number is 3.5 times 10 to the power 11. Now let's regenerate the response vector with new design matrix. Okay. Now we can see that it is not a perfect estimate. It is perfect up to 3 decimal place. So now the condition number is 3.5 times 10 to the power 11. So it is less than 10 to the power 12. So in this case, the keyword decomposition method giving, it is not giving the perfect match, but it is giving up to the estimates of beta is correct up to 3 decimal places. Now let's increase the condition number by the scale of 10 to the power 14. So it is greater than 10 to the 14 and less than 10 to the 15, the condition number. Now let's see what happens. see that the accuracy decreased. So instead of 5, that beta 1 is 4.88092, and instead of 10, it is 9.2499. So it is correct up to 0 decimal. And now try to increase the condition number. Oh, now the condition number is greater than 10 to the power 15. And your decomposition method also detect multicollinearity in the singular matrix. Since we have dropped collinearity equals to true, so that is why instead of showing that error, it is estimating betas, but it is that using the QR decomposition method, we are able to estimate only one parameter. So let's try that with Cholesky decomposition method. Again, it is showing that error. Now let's drop collinearity equals to true. So it will. Okay. Now you can see that the QR decomposition and Cholesky decomposition both detects multicollinearity in the design matrix. Okay. So what we have observed in this empirical examples, when the condition number is say 10 to, in the less than or equals 10 to the power 5, then your decomposition and the Cholesky decompositions both giving almost perfect results. But after that, the accuracy of the Cholesky decompositions decrease as the condition number of the design matrix increase till 10 to the power in the when the condition number is less than 10 to the power 12, the QR decomposition provides that exact estimates. But after that, as condition number increase, that accuracy using QR decomposition also decrease. And when we see that the condition number is greater than 10 to the power 15, then Cholesky decomposition as well as QR decomposition both detect multicollinearity in that design matrix. And previously we have seen that when the condition number is greater than 10 to the power 8, the Cholesky decomposition detects multicollinearity in the design matrix, that X prime X matrix. Okay. Now let's try a logistic regression with 5 millions of rows and 25 covariates. Let's randomly generate the design matrix and the response vector. And using benchmark tools, let's see what is that memory used by the QR decomposition and the Cholesky decomposition, and what is that running time of GLM with QR decomposition and the Cholesky decomposition. Definitely, we'll see that Cholesky decomposition will require less amount of memory, since the X prime X matrix, the order of X prime X matrix is only 25 plus 25. It is a small matrix compared to that X matrix, which is 5 million cross 25. So Cholesky decomposition will definitely require less memory, and pure decomposition will require more memory. So we can see that pure decomposition estimated memory size is 6.85 GB in this case.
and it took 21 seconds to evaluate the logistic regression, or 21 seconds to perform the logistic regression using keyword decomposition. Now let's wait for Cholsky decomposition. Yes, it is finished. You can see that only 2.12 GB RAM is required, and the time you can see that it is taking 7.467, so almost one third of your data. So, so what we can conclude from this exercise? So when we have very stable design matrix, the condition number of design matrix is say less than 10 to the power 5, then we can use Cholsky decomposition because it will give the same estimates but with less time and it will consume less memory. That's all. Thank you.